Hello everybody, in this video we're going to be going through activity 238, which is residential water supply. This is going to be a real world application of determining what we've been talking about, things such as static head, static pressure, dynamic head, dynamic pressure, Haas and Williams formula, using that to calculate out the head loss due to friction. So let's go ahead and let's begin here. We want to make sure, as always, we're doing an amazing job documenting all of our work, even this introduction, the background information. You want to be starting this off by having the actual title on here, and then going through, 238 residential water supply. And so you'll want to write that out. And then even as we're going through this, I'm going to highlight some things that you'll want to make sure that you've written down your engineering notebook. So we've got these goals here. We're going to be calculating out, just as we were saying, the static head as well as dynamic head for a water supply system. It's based on given parameters. We're going to also evaluate the head loss in a water supply line. This is going to be for the actual affordable home project. And then we're going to also analyze and solve water supply problems for different scenarios, ensuring proper water pressure and flow rate. So most people take it for granted that when they turn on a faucet, water is available. In fact, a lot of planning has been completed to ensure that homes and businesses have adequate water. Engineers use codes and calculations to ensure that source and pressure are adequate. Historically, civilizations in Rome and China were able to establish large urban areas and advance culture in large part because of their ability to transport large amounts of fresh water to citizens to meet their needs. So we got the presentation here for our procedure. The presentation is the one we went through in class, and then they tell us that we're going to be completing the following calculations for our affordable home. So they're going to give us a satellite image as well as a site image. The site plan, that's one that we've seen already, but that's just for reference. Remember, we want to make sure that we have the engineering formula sheet up as well, so I'm going to open that up in the new tab. I've also got the TI-84 calculator emulator up so that that's ready for us also. So these are the things that we're going to be calculating out here. So it is going to be guiding us through, but that's just to kind of give you a little preface of what all we're going to be calculating. Now, these water supply line facts, very, very important that we know these. So this is for our particular scenario, water supply line facts. So make sure that you have this written down. I'm going to end up doing a little speed through here. Okay, perfect. And so now we wrote down all of these facts that pertain to our situation here. So some things that I want to end up doing is I want to calculate out some information here. So I did see that the pipe length here is 3.12 miles. We do need to convert that to feet. And so let's go ahead and fire up the good old TI-84. We're going to take 5,280, multiply that by 3.12. We did forget to add in the 2 at the very, very end, so I'm just going to pop that in there. Perfect. So now we know that the pipe length, before taking into consideration the equivalent length, is going to be 16,473.6. Cast iron pipe is the type of pipe that we're using here. So what I'm going to do is I'm going to go ahead and pop down here to section 18, and so this is a cast iron pipe. Now what I am wanting to double check is to make sure that this is not a clean new pipe. So let's make sure. Yeah, the water line is 15 years old, so definitely is not a new pipe. So I'm guessing that we're going to end up using that typical design value. So we're going to go ahead and write down typical design value. C is equal to 100. So this is for typical design value. So they might end up telling us later on, right? Although we typically use this design value, they might tell us later on that we should use the lower range or the higher range of this, right? It's up to them. So we're going to kind of have that just written out for right now. Now, in terms of the equivalent length, we're going to do that calculation here. So I'm going to go ahead and do. So I'm going to pop that down here. So equivalent length, we have a diameter of our pipe is 8 inches. So let's go ahead and let's go here. So 8 inches. We have 7 90-degree elbows. So the 90-degree elbows, you'll remember, are right up here. So that's going to be 12. So 7 times 12 plus we've got 1 times that 45-degree flanged elbow. So regular 45-degree flanged elbow. See how it says flange fitting there? So we're going to go ahead and pop in here, and then that's going to be 7.7 feet for the equivalent length. And so now what we can end up doing is you could take your 7 times 12, right, plus 7.7, and we're going to end up with 91.7 feet. And remember, that is for the equivalent length there. This was for the length before we add in the equivalent length. And so to get our total length, we're going to have to add those two guys. So we're going to remember that later on. We also have Q, that's equal to 100 gallons per minute. So that's something else that is noteworthy that we want to end up mentioning. Alrighty, and so now that we have all these water supply line facts written out here, we can begin to evaluate this question. So for number 2, let's go ahead and scroll down here. So we have some sources here, right? We have the satellite image, and so they ended up taking the satellite image, they followed the water supply line, mapped that out, ended up finding that it's 3.12 miles in length, as mentioned. And then we have the actual site plan here. Now, some very important information is, what is the elevation of our site, right? They ended up providing to us the elevation at the lowest point of the water tower. However, what is the elevation of our site? If we end up looking at this image, it is a bit pixelated here and low resolution, but if we zoom in, you can end up depicting that that is 769 feet right there for our elevation on this contour line. And so we're going to end up going to a 769 as the elevation of our site for these calculations. Okay, so let's go ahead and let's calculate this out. So they want us to calculate the static head at the point of discharge under 10th Street, excluding head loss. So let's go ahead and let's begin. This is going to be 2A here, right? So we're going to calculate the static head at the point of discharge under 10th Street, excluding the head loss. So the elevation of the source, right? Source elevation, we said that that is 872.81 feet. We also have the discharge elevation, which is going to be the elevation of the site, right? So that's 769 feet. Now, if I were wanting to calculate out the elevation at point of water discharge, we're going to end up going 769 minus 6 feet. So we're going to go ahead and actually minus 6 on here. And then that's going to end up giving us 763 feet on that. The static head, then, we can calculate that out. Static head is going to be equal to our source elevation here, 872.81 feet, minus our discharge elevation, which is 763 feet. And so what we're going to end up with whenever we calculate this out, let's go ahead and punch it in here, 872.81 minus 763. So we end up with 109.81 feet of water. That's what we end up with there for our static head. So 109.81. So let's go ahead. Let's move on to the next one. B. They want us to calculate the head loss, including the losses for pipe fittings. So we're going to be calculating out, in this case, HF. Now, HF, as you may or may not remember, let's go ahead and pop into here. It is equal to 10.44 multiplied by L multiplied by Q raised to the 1.85 power divided by C raised to the 1.85 power times the diameter of the pipe, 4.8655. And so remember, as we're punching this into the calculator, we do want to use these big parentheses on the numerator as well as on the denominator to make sure that this is set up like a fraction whenever we calculate this out with our good old TI-84. So let's go ahead and let's get ready to begin. So first off, we have Q, right? So Q, we've got C, we also have, right, because we ended up finding that previously. Let's see here, C is equal to 100. They haven't mentioned anything about this being a new pipe still as we're reading through this. So we are going to use that typical design value for this. Excuse me. And then as we continue, D, the pipe diameter is 8 inches for this pipe. The only thing that we don't know yet is L, right? We do know the supply line length, which is, where was that guy? Where do we put that? Supply line length.
there we go, pipe length. So 3.12. So we are going to end up using that, and then we've got to add on that equivalent length that we've got. So let's go ahead and find out what that total length is that we're going to be calculating into here. All right, so L total, we're going to end up taking this 16,473.6 feet. And then we're going to add on that 91.7 feet. And so now we're going to end up determining what this total length is that we're going to be using. So 16,473.6 plus 91.7, we're going to end up with 16,565.3 feet. And so that is what L total is that we're going to end up using and punching into this actual formula. So let's go ahead, let's begin. So I'm going to put in the big parentheses here. It's going to be 10.44 multiplied by L, which is this value right here, 16,565.3. Then we're going to multiply that by Q. Q in our case is 100 gallons per minute. We're going to raise that to the 1.85 power. Close the big parentheses, divided by big parentheses again. C in this case, C is 100. So 100 raised to the 1.85 power, multiplied by the diameter of this pipe. The diameter of this pipe is 8 inches, raised to the 4.8655 power. And so now what we can do is go ahead and put this into our TI-84 here. So let's do it. So big parentheses 10.44. I'm going to move this over a little bit so you can see. 10.44 multiplied by 16,565.3 multiplied by 100. I'm going to press Shift and 6. That's going to allow me to go to the exponent there, 1.85. I'm going to press the right key on my keyboard, and then I'm going to close the big parentheses, begin the big parentheses again, 1.85, and then multiply that by 8, raise that to 4.8655. And so now we can find out what our head loss actually is for this. And so what we're going to end up with is we've got a value of 6.9809. And so what we're going to go ahead and call that is 6.98 feet. Remember, that is feet of water. So this is the amount of energy or the head loss due to friction. That's what we end up finding there. So now let's go ahead and pop back onto here. So calculate the head loss, we did that. Next, we need to calculate the dynamic head at the point of discharge under 10th Street. And so now, since we have our static head, right, we can calculate the dynamic head by subtracting this. And so in case if you don't remember, if you go right down here, dynamic head, so C, dynamic head is equal to our static head minus our head loss. And so now this is the case where it's 109.81 feet. Let me be careful with that. 109.81 feet minus 6.98 feet. And so what we're going to end up with here, 109.81 minus 6.98, we're going to end up with a dynamic head of 102.83 feet, and remember that is feet of water technically. And so now we can pop back on here. They want us to also calculate out the actual pressure as well in front of the house. And so now as we do this, all we need to do here is basically convert this, right? So D, so dynamic pressure, you'll remember, is just our dynamic head divided by 2.31. Now, why is it divided by 2.31? That is simply because there are 2.31 feet of water in 1 psi. All right. So now, if we end up taking that number that we previously got, that 102.83, we can divide that by 2.31. What we're going to end up finding is that we're dealing with 44.52 psi in terms of that pressure in front of the house there. Okay. So that's what we end up with for our actual pressure. Remember, that is synonymous to dynamic pressure. Actual pressure, same thing. So is the actual pressure sufficient for residential use, or should we have a pressure reducing valve installed? So the pressure that we've got here is acceptable, right? It is towards the lower end of that that range that we're provided. It is anywhere from 40 to 80 psi. And so if anything, you know, if there were 2 stories for this house, we'd probably want to increase the pressure a bit so that we have enough pressure to get up there to the second floor. But in terms of this, it's our affordable home, right? These aren't extravagant homes. These aren't huge mansions. These aren't 2-story buildings or 2-story houses, right? Just a single-story house. So I'm thinking that this should be pretty sufficient. So let's go ahead and write down the pressure is acceptable for residential use. A pressure reducer is not necessary. So a pressure reducer is not necessary. Alrighty? And I think I actually spelled that incorrectly. So we're going to respell that. There's a reason why I'm not a English teacher. Remember, anytime that we make a mistake, we got to strike it out single, and then we got to put the day's date, and then initials by that too. All right, so perfect. That's number 2. Let's go ahead. Let's move on to number 3. Is for question number 3, they say a facility that receives water at an elevation of 350 feet at the water meter is 4.1 miles from the water tower. So let's go ahead, let's write this down here. So question number 3 is what I'm going to do. Question number 3, or step number 3, they have it where the facility receives water at an elevation. So what we're going to do is this is the discharge elevation. So that's going to be equal to 350 feet. This is from the source elevation. So the source elevation is that water tower, right? So the water tower is 527 feet there. That's what we've got. Flow rate, we've got Q is equal to 110 GPM. And then they say that the diameter for this particular scenario in this question that we're doing is an 8-inch pipe. It's ductile or cast iron with flange fitting. So what we need to do is we have C. And so let's go in here. Let's find C. So cast iron. Did they make the designation of it being a new pipe? I don't think so. Let's see. Let's make sure. Yeah, it doesn't say anything about it being a new one. So we're going to end up using that C value of 100. Very good. So they tell us it's the flange fitting. So remember, we got to be using this right here. And the diameter of this pipe is 8. So now let's go in here. Let's go ahead and find out. So distance, the length, 4.1 miles. We're going to multiply that by 5,280 feet because that's how many feet are in 1 mile. That's going to cancel out our units of miles there. So miles and miles going to cancel. We're going to be left with feet. So now let's go ahead and do that. Let's perform that calculation of 4.1 times 5,280. That is going to be 21,648 feet. Now we've got to calculate that out for the equivalent length. So the equivalent length we need to find, we have 2 90-degree elbows. So let's do this for the good old 8-inch. Right here we've got 2 90-degree elbows. So that's going to be 2 times 12 plus, let's go ahead, let's pop back in here. We've got 2 gate valves, so 2 times the gate valves value. So valves, gate valves right here, and we can see that that's 3.2 feet, equivalent length per gate valve. We've also got, 17 line flow T's, quite a bit here. So 17 line flow T's. So we can go to T's, so we see line flow 4.7, so 17 times 4.7. It's racking up quite a bit of the equivalent length here now. 6 of the branch flow T's. So let's go back into here. We got T's, branch flows down here. That's 24, so 6 times 24. Plus, we've got 1 swing check valve. 1 swing check valve. And so that's all the way down here. And we can see that that's 90 feet equivalent length. Wow, dang. So we're going to end up adding all these out. So let's go ahead and let's do that. So we got 2 times 12, that's just 24, plus 2 times 3.2, 6.4, plus 17 times 4.7, 17 times 4.7. That's going to give us 79.9. Then we've got 6 times 24. Now, if I were you all, I would just be punching this in, right, so that you got it. But I'm going to break it down into each step, so then that's 90. So let's go ahead and do this. So we got 24 plus 6.4 plus 79.9 plus 144 plus 90. So that's going to give us an equivalent length of 344.3 feet. So that's the equivalent length there. Now remember, to get our total length, so total length, we've got to go ahead and add up that previous length plus the equivalent length. So we're going to do 21648 feet plus 344.3 feet. Now if we do that, we can punch that in the good old calculator. 344 plus 3, I'm just going to put the plus because that'll make sure our answer is used for that. And then now we can add this up. So 21, looks like I forgot that, 21648. Nice, plus the answer, that's going to end up giving us 21,992.3 feet. So that's our total length there that we're going to end up using for our Haas-Williams formula. All right, so now let's go ahead and let's see what they are wanting. So the water flow, the water supply line includes the following. Okay, so they haven't prompted us for what we want to solve for yet. So now we've got to find the total dynamic head. So remember, dynamic head, that's the actual head, right? Then they also want the dynamic water pressure, which is also the actual water pressure at the meter or at the water meter of this facility, okay? So they also ask, what is the static head at a sink on the second floor if the sink faucet elevation is 14 feet above the meter elevation? So basically the discharge elevation, instead of it being 350, we're going to add to that 14 feet to determine that. Okay, so let's go ahead and let's pop on here to our equation sheet before we get started. And so now dynamic head, as you remember we were talking about it in class, is equal to the static head minus the head loss, right? And so where we want to start even before that is we want to end up determining what static head is, right? And so static head is the change in elevation between the source and the discharge. So what we can go ahead and do here is we can write out static head. And I'm going to put in parentheses here. This is equation 16.2, right? So static head is equal to, well, it's the change in elevation, right? So it's our source elevation, 527 feet, minus our discharge elevation, which is 350 feet. Now, if we end up subtracting these two, we can punch into the good old calculator. 527 minus 350. That's going to end up giving us 177 feet. So that is our static head there, right? So a static head is equal to 177 feet, okay? So now that we have our static head, what we can do is start to try to calculate out our dynamic head, okay? So now I'm going to flip this on over, put number 3, and I'm going to put in parentheses here, continued. And so now what we want to do is we want to actually write out dynamic head. And then this is equal to, so we've got static head minus head loss. Now, do we know the head loss yet? No, we do not. Remember, what is head loss? That is HF, right, which is our Haas and comes from our Haas-Williams formula. And so the static head, though, we do have that. Now, the static head, we just proved that is 177 feet of water, right? So I'm writing down the feet. That means feet of water minus, and then we got to do HF in this case, right? So why are we putting in HF? That's because that is the Haas-Williams formula. That's how we calculate out the head loss due to friction. So we're going to put a little pause on this for right now. It's going to be 177 feet minus, then we're going to come back, whatever we calculate HF out to be, that's what we're going to put in there, okay? So HF is equal to 10.44 times our length. Remember, that is the total length, and so that's after we add in the length here, the supply line, plus the equivalent length. And so what we end up with is 21,992.3. Okay, so let's double check that, make sure we're good. Yep, so that is it. Remember, that is not raised to any power here. And I'm going to zoom in on our good old Haas-Williams formula so we can get a nice view of this. So we're going to take L multiplied by Q. Now, what is Q? We're going to be doing a lot of flipping around here. So Q, remember, this is the water supply line facts. We don't want to be focused on that. We're going through number 3. It's 110. So let's put in 110 gallons per minute. Remember, that is raised to the 1.85 power. Then we can put this right here on there. Remember, whenever we do put this into the calculator, we want to use those big parentheses for the numerator, and then the denominator is going to also have those big parentheses. So we're going to go ahead and take C, which was a value of 100 for this particular example. So we're going to take 100, we're going to raise that to the 1.85 power, and then we're going to multiply that by our diameter. Our diameter in this case was 8 inches, so we're going to go ahead and put times 8 raised to the 4.8655. Remember, close of the big parenthesis. And so now what we can end up doing is we can punch this into our calculator. So I'm going to press Shift 9. It's going to bring up the big parenthesis there, 10.44 times, we're going to go 21992.3 times 110. Remember, if I press Shift 6, that's going to allow me to put in the exponent. We're going to raise that to the 1.85. We got to press right on the keypad. Then we're going to put in the big parenthesis again, divided by big parenthesis again, 100, Shift 6 to get to the exponent, 1.85. Press the right key to get out of that exponent, times 8 raised to the 4.8655 power. And we're going to do that. So what we end up finding, wow, 11.055 feet. And remember, that's feet of water. That's what HF is equal to here. So that's the amount of head loss. So we're going to go 11.055 feet. And so now whenever we end up calculating this out, right, we can take our 177 minus that answer that we just got, right? And so now that's going to tell us our dynamic head or the actual head. So that's 165.94. And that's feet of water, right? So I'm going to go ahead and inbox that answer. So that is the feet of water. So that's our dynamic head. And so that's what they were asking us. They also want us to calculate out the dynamic pressure. So I'm going to go ahead and put dynamic pressure in here. Now remember, dynamic pressure, that's basically our dynamic head just converted to PSI, right? And so what we can do is take our dynamic head, divide that by 2.31. Why is that? It's because in 1 PSI there are 2.31 feet of water. So we can take this value here. Let's go ahead and do that. So we're going to take our previous value. Now I'm going to use the actual answer. And so we're going to divide that by 2.31. And so we're going to press enter. What we're going to end up with for our actual pressure is going to be 71.8, and I'm going to put 4 PSI. And so we're going to inbox that too because that is our actual answer there. So the dynamic pressure is 71.84 PSI. Now, is this within the range where it's acceptable for residential purposes? Absolutely. It could be anywhere from 40 to 80, right? So this is at 71.84. It's a little bit closer to the higher end, but especially because this is a second floor house, it's probably a good thing that we've got a little bit of that higher end pressure. So the next part, what they're asking us is what is the static head at a sink on the second floor if the sink's faucet's elevation is 14 feet above the meter elevation. So static head, remember, that is equal to the source elevation minus the discharge elevation. We'll remember that we had 350 there for that. So 527, that was that water tower. Then that's minus, now we're going to put in brackets in here. Now, why are we putting in brackets? So the actual elevation of the House is 300, or the water meter is 350 feet. Now we are going to be 14 feet above that. So we're going to add on the 14 in there. So now what we end up with is going to be 364, right? That's subtracted from 527. So now we can go back in here. We can go 527 minus, and then we got 350 plus 14, which we said is 364 there. So 527 minus 364, that ends up giving us 163 feet of water. for our static head. Now, do they ask for the static pressure? They do not. So, 163 feet, and what we had at the first floor is 177 feet. And so what's happening here is we are losing pressure, right, as we go up. So that sink faucet doesn't have as much pressure, doesn't have as much head, static head, as the previous, okay? So let's go ahead, let's move on to this. What they read on this next part of this problem is the water supply line from the meter to the house and up to the second floor sink is a 1-inch copper pipe with screwed fittings. This is where we've got to be very, very careful. We've been talking about so far how we've been using the flange fittings, right? If you go right here, you'll see screwed fittings are right here, and this is where we've got the 1-inch pipe, right? And be careful, this is copper, as well as the designation of the material type here. So we can end up in-house water line info. So we can go ahead and document this, right? So this is the in-house. So we've got diameter D is equal to 1 inch, and we also have C, which is a material for copper, right? So if we go in here, we can find for copper, I'm guessing we're going to be using the typical design value. So let's see here. Let's make sure that doesn't say that it's a new copper pipe. No, it does not. So we're going to end up going on here. And so this is for the typical design value, it's 130. So C is 130, and why is that? Because it is copper. So I'm going to put that in parentheses too. Now, additionally, what else do we need to end up writing down? Let's hear. So screwed fittings. So the pipe from the meter to the second floor is a total of length 75 feet. This is nice. They don't give us that in miles. But then we do have to do that equivalent length calculation. It is for 4 line flow tees. And then we've got a swing check valve, so we're just going to put in a single parenthesis there. And then we've got 7 regular 90-degree elbow turns. So let's go ahead, let's pop back in here. We got the screwed fittings. This is for a pipe diameter of 1 inch. So we've got 4 of the, let's check it out. What is it? 4 of the line flow tees. So we're going to go to tees, we're going to go to line flow. We see that that is 3.2 feet for the equivalent length. Then we've got 1 swing check valve. So we're going to go to valve, swing check. That's going to be 11 feet as the equivalent length. And then we've got 7 of the 7 regular 90-degree elbows, so it's the same case as our flange fitting, it's just the first row. So 7 times 5.2. So now we can end up determining what our equivalent length is here. Let's go ahead and punch this into the good old handy-dandy TI-84. 4 times 3.2 plus 11 plus 7 times 5.2. Perfect. Calculated that out. We've got 60.2 feet. Now, guys, this is pretty crazy. Our actual length of this was 75 because of all these screwed fittings we have in here. Our equivalent length is almost just the same as the actual length of the pipe that we have already. So remember, we can determine the total length, and so L total, that's going to be equal to our equivalent length plus that previous length that we've got. And so what we can do is we can just add on to here. So answer plus, is this guy going to work? Let's hear. Plus, oops, let's try this again. Plus, there we go, nice. So 60.2 is our equivalent length. We're going to add on that 75. And so now we've got 135.2 feet. And so that's what we want to use for the Haas and Williams formula here, right? And so let's go ahead and let's determine this. We've also got some other information we need to know. Q, what's good old Q? A flow rate of 10 gallons per minute, so pretty slow flow there. Let's go ahead. Just did a quick Hollywood style wardrobe change where I spun around, changed shirts. Anyways, let's go ahead and let's get back down to this. So what we need to do now, so remember, this was at the sink, right? This is at the sink. And so now what we can do is we can calculate out head loss. So HF, that's what we're going to be calculating out here. Now HF, in terms of HF, we need to use the Haas and Williams formula. So let's go ahead and let's bring this up here. So the Haas and Williams formula was HF equals 10.44, this guy right here, 10.44 multiplied by L multiplied by Q raised to 1.85 power, divide that by C raised to 1.85, and then multiplied by the diameter of the pipe. 4.8655 is that power that is raised to. And so now we can end up plugging in our values. Remember, we want to use the big parentheses here on the top for our numerator. So our total length here that we're going to be plugging in is going to be that length of the supply line plus the equivalent length. And so we end up with the 135.2 feet. Then we need to multiply that by Q, which is our flow rate for this copper pipe. Flow rate is a minor 10 gallons per minute, right? So not too many gallons, not too high of a flow rate there. Divide that by, remember we want to use the big parentheses again on this bottom, We're going to plug in C. C for our copper pipe was 130. We're going to take 130, raise that to the power of 1.85, multiply that then by D, which was just 1 inch, right? Now 1 raised to this power, just, we'll end up calculating that out. And so let's go ahead and punch this into the calculator here. So 10.44 times 135.2 times 10. Remember, shift 6, that allows you to put that to the exponent in the emulator. We'll press right to get out of the exponent. Close the big parentheses, divided by big parentheses again. 130 raised to the 1.85 power times 1 raised to the 4.8655. And then now we can go ahead and multiply this out. So what we end up finding is our head loss here is 12.27 feet of water, right? So that's what our head loss is there. Now, let's go ahead, let's calculate out total head loss from tower to the sink. Now, in terms of the total head loss, though, from the water tower to the sink, it is going to be the case now where we have this 12.27 feet of water, right, that we're losing just whenever it's inside the house, right, once it goes through this copper pipe. But then also we have the head loss that was from our previous 8-inch diameter iron pipe as well, right? And so what we can do is we can calculate out that total head loss. So total head loss for this is going to be that 11.055 feet, and then we could put in parentheses here 8-inch iron pipe, right, plus this 12.27 feet, and then that's going to be the 1-inch copper. And then we can end up determining what this total head loss is here, right, by adding these up. So we could take the 11.055 plus that 12.27, and what we're going to end up with is 23.33 is what we're going to call that feet of water that is lost in total, right? And so quite a bit there. And so now what we could do is we can calculate out that dynamic head. And so the dynamic head in total, this is going to be the actual water pressure, or the actual head is what we can call this. Now remember, that's the static head, and then that is minus our head loss. Now in this case, that static head is going to be the 163 feet that we've got here. And then we want to minus the amount of head loss, which is going to be 23.33 feet. And so now what we end up with here is going to be 163 minus 23.33. So now we got 139.67 feet of water. So that's the actual pressure that we're dealing with there, 139.67 feet. And so now what we can also do is we can find that actual pressure, right? So if we take this and divide it by 2.39, we can determine the actual pressure. So we'll go right here, actual pressure. Remember, that is the 139.67 divided by 2.31. So we could put that in here, 139.67 feet, divide that by 2.31. Now we're going to end up with, for that actual pressure, 139.67 divided by 2.31, the actual pressure we're dealing with here is roughly 60.46 psi. So now we can go ahead and inbox this answer. We'll also box this answer. We'll also inbox this answer there too. And so what we can conclude here is after this water travels from the water tower, goes through the city's water supply system, reaches our house, goes up to that second story through that 1-inch copper piping, we're going to end up finding that the actual pressure that it's leaving that sink is going to be 60.46 psi. All right. Hope that was helpful. Hope you guys enjoyed following along with these calculations on this little journey that we went on. Happy calculating to you all, and catch you all in the next video. Bye-bye.